Now, let's think what is happening on a piece of land. Now here, say for example, you are growing these crops here and you are exposing them. So here you have a piece of land, and through 3 different seasons, by the way, in Indian subcontinent we grow crops thrice in a year, which we call as a kharif crop, which is the rainy season, where the sowing will be happening by the end of July somewhere. In some places it happens slightly earlier depending on when the monsoon is arriving, and this lasts for next 90 days to 120 days, August, September, October. Probably by November the harvest takes place. Then comes the next season, which is called the Rabi season, which is the winter crop, where we grow wheat. So in the Kharif season we grow the rice, paddy, mostly across the country. Then you have the wheat crop, which is during the cold months, winter months, January, February, March, and then of course we harvest it. Then comes a spell across the country, which is kind of a dry spell. That's what is called the Zaid, or the summer crop, ZAID. So you have Kharif, Rabi and Zaid. So which is around April, May, June. That is the kind of where very few really go crops. We rather depend on vegetables during that time. And here you have the rainy season, and this is the winter, which is mostly dry in India. So these are the 3 cropping seasons we follow mostly across the country. So now here you have a piece of land, some hectare something, and you are growing a crop, say A. In one season, say for example in Kharif you are growing A, in the Rabi you are growing B, and say in the Zaid you are growing P. Fine. And this cycle continues. So if I see, so this is somewhere from July to November. Then you have from say November or December to April, or March, somewhere around March or April, and here from April till June. So round the year, if you see it, we are growing crops. Now, as we are continuously growing crop, as I told you, we are depleting the nutrients. So now, while we are depleting the nutrients, we are applying fertilizers. And the story of fertilizer, if I have to say, the modern days agriculture, major ones which are used: nitrogen, phosphorus, potash. And if you look at it, nitrogen, the critical one, nitrogen is synthesized by an enzyme called nitrogenase. Nitrogenase by the biological world. There is enormous amount of nitrogen in the air, but we really cannot trap it, barring aside rhizobium or symbiotic microbes. We'll talk later about it. Okay, they are the ones who can fix the nitrogen from the environment and convert it into a nitrogenous compound or nitrogenous form, which could be made available by the plants. Now, that's not really sufficient when we are talking about growing crops round the year. So you have to add more nitrogen, and historically the breakthrough happened in the very early part of 1900. This is the time the major breakthrough was Haber's process. Which changed the concept of growing crops. This is where we could synthesize different nitrogenous compounds. Haber process is a landmark discovery, earlier part of 19th century. Bosch and Haber process. That changed the way we do agriculture for last almost now 100 years. We had sufficient amount of sources to produce ammonia, urea as a source of nitrogen, followed by potash, phosphorus. So, these compounds in the form of salt now started to dominate the modern agriculture since 1900, early part of 1900. Now, these are man-made chemicals and they have a turnaround time to mix up with the soil, get acclimatized with the soil. But of course, the plants are pulling them through. But now think of a situation. In the very first part of my lecture, I told you that we need organic matter to trap these things so they could be slowly released. So while we were adding all these kind of things, many soils in many parts of the world were not being sufficiently supported with organic matter. And what happened is, because of not supplementing sufficient amount of organic matter, these excess nitrogen or phosphorus or even potash started going down the soil and tried to get mixed with the water table. And eventually they gutted the water table in such a way that the nearby rivers or ponds or the water bodies had excess nitrogen, excess phosphorus, much higher than their tolerable limits. That led to lot of unnecessary growth, excess growth of excess vegetative growth in the water bodies, thus creating a lack of oxygen situation. Apart from contaminating or polluting the water bodies, which includes your ponds, rivers, streams, so you realize that though we have no other option, we have to depend on all these, but how much are individual plant needed? Are we using them in excess? That's a very big question which is now being posed in front of agriculturists and plant biologists. Are we really putting way more? And this is where there is a question which is coming, a concept which is evolving in the horizon of futuristic agriculture called which I have mentioned, but today in a different context I am coming: precision agriculture. I told you the problem that we are applying these compounds in excess. I have to find out a way to reduce that excess. How we can do it? Could we ensure, say for example, somewhere or other, could we ensure, suppose here I have a plant which is growing, okay? These are the shoots, and could I ensure that my required compound or chemical remain concentrated in this region, or I do a foliar spray or some way or other, it works. So lesser concentration. Second thing, what happened? Because of this kind of situation, many of these plants started to grow much more than their limits, which eventually attracted more infestation from this part of the game: insects and microbes. So this leads to excess use of insecticides and pesticides. Now the problem of using excess insecticide and pesticides is they become part of food chain, because when you are putting them, unless otherwise they are metabolized by the plant, they will remain either in the fruits or in the stem or in the leaves or in the roots, and we consume all of that. We consume the root of some plants, we consume the shoot of some plant, we consume the underground fruits of some plants, we consume the fruits of some plants, we consume the leaves of certain plants. So unless otherwise, the insecticide or pesticides or microbicides, whatever you call it, are the kind that a plant has the ability to degrade it during its lifespan of, mostly the crops are of, like, unless it is sugarcane, which is 9 months or 10 months crop, most of these grain crops are like 90 days to 120 days and so forth. Unless they can metabolize all these things, degrade all these compounds, they will remain within the plant system, and this is a serious concern for several hormonal disbalances which affects the female population big time because of the complex hormonal milieu, and of course the male too. So there are several diseases which erupt because of the residues of these compounds which are found in the food products. Similarly, if these are used for the fodder crops, a lot of it goes into the animal side, and which eventually becomes, it's very interesting, like if you think that there is always a debate among the vegetarian and the non-vegetarian, but the thing is that the whole gamut of agriculture affects both of them equally. Say for example, there is an example of a, say, fodder crop, okay? Now a fodder is getting, say, some form of insecticide or fungicide or something. So now this is consumed by an animal, say a cattle. Now we are deriving milk out of it, say. So milk will have the residues of this traveling, or using it for, say, meat, okay, or even say eggs, okay. So these residues are traveling along, unless otherwise the fodder metabolizes it or the animal metabolizes it. But most of these compounds are not so easy to metabolize. So whether you are a vegetable eater or you are a non-vegetarian or you are something like this, only a milk and plant, no one is spared in this game. Third thing, when we talk about weedicide or herbicides, these weedicides or herbicides are again having the same fate, same problem, because they become part of the plant and which moves into animal, and whereas they travel along. Well, the situation is not grim. It is just we have to realize what is that amount which is precisely we can put, which we can tolerate or which will go away. But if we do it in excess, there are always possibilities that we may hit the wrong chord and eventually we'll have to solve other problems which are much more relevant to the medical world. Okay. Now if you look at it out here, so we talked about the challenges, what is there with the insecticide and pesticides. We talked about the challenges of having fertilizers. We talked about the challenges of weeds. Now think of this situation. Because of percolation along of different compounds or chemicals used in agriculture, we now land up with another problem, which is clean water resource. And agriculture cannot be done without water. So that's why you will see there is a section in this course where we talk about nanotechnology in water purification. The world where we are continuously contaminating the water because of these compounds needed to be cleaned, because this is one resource which, unless otherwise we have technology to convert seawater or saline water into fresh water, we have a finite resource of fresh water, and we have to work with that fresh finite resource for generations to come, unless otherwise we make breakthroughs in water purification, which is happening, but scaling up is equally slow. Like if you visit places like Israel, they do tremendous amount of water purification because they do not have much resources. They have to do it. Similarly, there are other places where water is one of the most challenging community, or even if you go to places like Bombay and other places where you have limited supply of water. It's not that you will get water all throughout the day. There is a rationing of water, but that's just to, at this stage, to counter or to ensure everybody gets it. But that's not who as human race we are. We have to find out technologies, we have to find out ways to counter these kind of challenges so that our generations to come will have ample resources to think bigger stuff, not to depend on these simple things, right? So on one hand, we realize that we do not have an option. We cannot go back. We cannot put the clock back that will become something like we started as nomads, will become nomads, or we will burn piece of land and move on to the next one. Those options are not there. Those are impractical situations. Instead, what we have to think is how precisely we can use these chemicals in agriculture, which includes crop production, vegetable production, fruit production, fodder production, all the way to animal production, poultry, dairy, meat, and even leather, as a matter of fact, yet ensuring the assisting resources like land, water, environment is being conserved, we use it, but we replenish it with our scientific technical know-how.